Hello, my name is Santiago Rios, and this is my presentation on X-ray diffraction analysis, the powder method, and I would like to concentrate on aviation coatings, on one specifically that I use on a day-to-day basis. A quick description of X-ray diffraction powder analysis is basically a technique is used to analyze and detect phase identification. We can also determine the dimensions of each unit cell for that compound. Usually these compounds are of crystalline material, and basically diffraction is just the scattering of X-ray crystals. And a quick description and process flow of how X-ray diffraction can help us is you'll shine X-rays through that crystal below. You'll get some type of diffraction patterns. You can then create an electron density map, and then with this you can create an atomic model. The principle of X-ray diffraction is, like I mentioned, is a focused X-ray that's shot in an angle. This angle is called the angle of incidence. The way these X-rays reflect off the electrons, the atoms, as you can see in the below pictures, the green circles are the atoms, the blue are the X-ray beams, and the diffracted angles are in red. The equation that you see that's Bragg's law, and is basically what controls X-ray diffraction. The deflected angles and intensities are measured, and with this you can basically identify a compound's crystallinity and crystalline size. Each compound, each material does have its own pattern and is very unique to themselves. Here a quick picture. You see an X-ray beam being shot at a sample crystal. The scattered X-rays then hit an X-ray detector. This pattern or diffracted X-rays create a pattern, and you can see that pattern here at the bottom left, where you see tiny bright dots. Those are actually locations and atoms within that crystal. Sometimes you get a circle, and that gives you more of a visualization of how the atoms are stacked for that compound. And you can interpret this data very easily using the Bragg's law, 2 theta versus intensity, which will get peaks. These peaks represent planes within that compound. You can have, for example, 100 to 11 planes depending on the peak. Some of the quick applications, like I measured, you want to test your sample for purity, making sure it meets quality standards, making sure that for example, we spray that powder, it is within its limits and standards, and it's not going to create any damage to any parts. We can also measure any impurities. Most likely it will be present, but at a minimal, making sure that this minimal impurities is within acceptable standards. And we can also do particle size distribution. This is something that I use on my profession in a day-to-day basis, making sure that the particle size distribution for the powder that we're going to be used is acceptable. Like I mentioned, particle size distribution is a function. This states the amount of mass and particles that are present according to the size on that field of view. Particle size distribution determines the chemical and physical properties of that powder, and all these physical and chemical properties of that powder does have a standard, so we are checking against a standard. It affects the powder strength, it affects the load-bearing properties, and it affects chemical reactions. Here in your bottom left, you see your particle size distribution formula, your wavelength, angle of incidence, and your peaks. Here's a quick snapshot of what that field of view looks like in terms of particles, the size of the particles, and the range in which you need to count the amount of particles present for that type of range. And once again, the data you can obtain it through this Scherrer formula to get your particle size distribution for that range. Some of the quick pros and cons for X-ray diffraction powder analysis is your strength. Basically, it's a very fast analysis. Usually takes about 20 minutes to set up and implement from start to finish. You don't need a lot of sample preparation, only minimal, and that minimal, and you'll see it in the limitation section. Um, the strengths is you can provide unambiguous mineral determination, making sure it meets physical and chemical properties like I mentioned, and the data is very easy to interpret. So the limitation is you need to ground that powder so it fits that holder. Detection limit for mixed materials is about 2%. It only works for homogeneous, or the best results are for homogeneous and single phase material. And you do get a high angle reflection issue when it comes to peak overlay. At high angles, that's when you get two peaks over two peaks, where it can be problematic to determine which plane is that. A quick one. This is a description of thermobaric coatings. I think many of you know what a thermobaric coating is, but just to kind of go over it. The most commercially used is the yttrium stabilized zirconia, which is a thermal insulation that is applied on parts that go into the hot section of the engine. It protects from oxidations at high temperatures. It does protect as well from corrosion. It does have a high thermal expansion coefficient and a low thermal conductivity, which makes it great for these hot environments inside the engine. The structure of a thermobaric coating is the metallic bond and a ceramic top coat. The ceramic top coat is that yttria stabilized zirconia that I want to talk to you about. Here you see representation of the substrate, your bond coat, your thermal growth oxide, and your yttria top coat. Here, in a study that I read, we were able to find out that YSZ exists in various structures. Percentage of moles from 3 to 40 was studied, and we were able to see that at 3YSZ there was a thin film tetragonal present, but at X-ray diffraction it was a combination of monoclinic and tetragonal. It is a single phase, and once that phase changes, it's no longer heterogeneous. At AYZ, it goes from tetragonal to thin film cubic structure. At 20%, you do have a cubic structure of at XRD, but it does maintain its cubic structure when it goes to a thin film deposition process. For the 40% is where it was interesting. You see your rhombohedral delta phase. It does a phase change from cubic structure. This is due to point defects in the lattices. It does create a high mobility during these lattices, and that's why it creates such a drastic structure change. Here's a summary. You'll have your powder target at the bottom, your tetragonals, your cubic, and your rhombohedrals, and you have your phase changes are notified by the wiggly squiggly line, and you have a straight line which is basically retains its properties. Here you see an X-ray pattern diffraction for the percentage of 3, 8, 20, and 40. All samples show a large degree of ordering, but not in the case of 40YSZ. No ordering is present. Here at the bottom you see that the lattice parameters doesn't change for any of the samples. For your 3, 8, 20% is about 0.051 to 0.53, and this is due to usually the plane 002 is usually located in the same position when it comes to all the percentages of yttria. Here you see your peaks and valleys, your 2 theta for intensity and units. You see that the 3YZ has the lowest yttria content, and that's why you have more peaks. Your 8% is more of a simple diffraction chart. The funny or interesting aspect is that the 20% is identical to the 8%, which we find interesting. The one that is drastic change, like I mentioned throughout the presentation, is the 40%. Here you see a lot of peaks throughout the 2 theta range, and this is due to the ordering. This is due to the the lattice, the high mobility that is present. So here you have your intensity versus 2 theta, like I mentioned. And I wanted to quickly go over what the presentation was about. I wanted to tell you what X-ray diffraction is, the principle, its pros and cons, and wanted to explain to you what thermal coating is and pick one of those commercially available thermal coatings and do a quick X-ray diffraction description analysis study for it. That's about it for my presentation. Here are my references, and thank you so much for watching.